Now, in this video, we will going to discuss about the problem on a composite bar. The problem reads as a rigid bar weighing 1 kilonewton supports a vertical load of 4 kilonewton at its midpoint. It is attached to the fixed ceiling using a steel wire of diameter 3 mm and two aluminum wire each of 5 mm as shown in figure. So the figure is here wherein you have three vertical bars, one of steel and other two of aluminum, whereas the steel wire has a diameter of 3 and having a length of 800 mm, and two aluminum wire, this one and this, which has a length of 500 mm and the diameter is 5 mm. So what are all the things which we need to find out? We need to find out the stress in steel and aluminum wires and load carried by each wire, and also the distance moved by the rigid plate or the rigid bar, which will going to come down due to the application of load. The Young's modulus for steel is 200 GPa and Young's modulus for aluminum is 70 GPa. So this is the problem which is given to you. So we need to solve this problem. So to do that, so first we will going to consider the data. So the data is diameter of steel wire is 3 mm and the diameter of aluminum wire is 5 mm and length of the steel wire is 800 mm and length of the aluminum wire is 500 mm. And the Young's modulus of steel is 200 into 10 to the power of 3, which is 200 GPa, and Young's modulus of aluminum, which is 70 into 10 to the power of 3 Newton per mm square, and also the load, which is 5 kilonewton, which is load applied at the midpoint, which is 4 kilonewton plus, and the load of the rigid plate, which will going to act, both will going to act downwards. Since it is acting downwards, naturally it's going to be the positive because of the tensile load. So now we will going to consider the problem. Now how to find out that the stresses in the steel and aluminum wire. So to do that, first the condition for the total load on the bar will be equal to load on the steel wire plus the load carried by each outer aluminum wire. So that is that PS, let us take for now that we will assume that PS is the load carried by the steel wire and PA is the load carried by the aluminum wire, and capital P is the total load. So capital P, which is the load carried by the steel wire, which is the total load, will going to be the load which is acting at the midpoint and also the load carried by the rigid plate, which is 1 plus 4, which will going to be the 5 kilonewton, which is 5000 Newton. So what is the condition here? Since we are assuming that PS is the load carried by the steel wire and PA is the load carried by the aluminum wire, since you have two aluminum wires and one steel wire, so naturally PS plus PA is equal to the total load, which is P, which is now that what happens when you take that. So the symmetry, the outer aluminum wires will carry equal loads. So now here PS plus 2PA is equal to P, which is 5 into 10 to the power of 3 or 5000 Newton. So PS plus 2PA is equal to 5000 Newton. Now we will going to substitute the value of PS. That means the PS is nothing but stress is nothing but the load by the area of cross section. Since he has already given the load, we are substituting the formula of PS as sigma S into A, because sigma is equal to P by A. So P is equal to sigma into A, which is the general equation or the general formula. Since the load carried by the steel wire, so the stress in the steel wire into the aluminum of steel wire, area of cross section of the steel wire, plus 2 into again the load carried by the aluminum wire will going to be the stress of aluminum and into area of cross section of aluminum. So that will be equal to 5000 Newton. Now, so we will going to substitute. So we will sigma S into, that is the stress on the steel wire multiplied by the area of cross section. Since he has given the diameter, so naturally the area of circle, which is pi by 4 into d square, plus then we have 2 into sigma a into pa. So here sigma a into aa, 2 into sigma a into what is the area of cross section of the aluminum wire, which is again pi by 4 into dA square, which is equal to 5000 Newton. Now then you substitute the value of ds and dA in the equation. So what happens? Ps into pi by 4 into 3 square plus 2 into sigma a into pi by 4 into 5 square. So you can take the pi by 4 as the common factor, and so what happens once you take pi by 4 as the common factor, then sigma s into 3 square plus 2 sigma a into 5 square, which is equal to 5000. So once you take pi by 4 as the common factors, the 4 is cross multiplied to the numerator, and pi is cross multiplied to the denominator. So therefore, in this equation, you will going to get it as sigma s into 3 square plus 2 sigma a into 5 square, which is equal to 5000 into 4 by pi. Now, once you do that on simplification, so when you expand this, 3 square becomes 9. 9 into sigma s plus 25. 5 square is 25 into 2 is 50 into sigma a. Even on simplification, this term we are going to get it as 6366.2. Now, as we know, now also we know the deformation in the steel bar is equal to deformation in the aluminum bar. So assuming that the bar remains horizontal even after the stretching. So what is the delta L? The delta L formula, it is the general equation, which is P into L by A into E. As we know that the deformation of the steel wire since it is the deformation of the steel wire, so we are going to consider as P into L by A into E as PS into LS by AS into ES. So that is what we have written here, PS into LS by AS into ES. So that will be equal to the deformation in the aluminum wire. So that will be equal to PA into LA by AA into EA. But we know the PS by AS as sigma S. So that is the stress, which is the definition per the definition. So sigma S into LS by ES is equal to sigma A into LA by EA. So that is what we are going to get here. So what we have done is express this PS AS in terms of sigma S into LS by ES, that is equal to PA by AA is nothing but sigma A into LA by EA. So that is the aluminum wire. Now you substitute the values of the length of the steel wire, which is 800, and the Young's modulus of the steel wire as 200 into 10 to the power of 3. And also the length of the aluminum wire, which is 500, and also the Young's modulus of the aluminum wire, which is 70 into 10 to the power of 3. So on simplification, you will going to get it as sigma A will be equal to 0.56 into sigma S. So this is the term you are expecting sigma A in terms of sigma A as 0.56 sigma S. Now you are going to substitute the value of sigma A as 0.56 into sigma S in this particular equation. So what happens? 9 sigma S plus 50 into 0.56 into sigma S is equal to 6366.2. So now on simplification, what we are going to get as the stress in the steel wire, which is sigma S, will be equal to 172.06 Newton per mm square. Always the stress is load by the area of cross section. The load is Newton, area of cross section is mm square. So naturally the stress will going to be sigma S 172.06 Newton per mm square. Now similarly we are going to calculate the stress in the aluminum wire, because we know that stress in the steel wire, which is multiplied by 0.56 into sigma S. So that is this expression. You substitute the value of sigma X as 172.06, and also 0.56 is the constant. So 0.56 into 172.06, which will be equal to 96.534 Newton per mm square. Now, then the load carried by each wire. So which are all the loads which are carried by the each wire? One is the load carried by the steel wire, and also the load carried by the steel aluminum wire. So what is PS? The load carried by the steel wire, which is PS, is equal to sigma S into AS. You know the value of sigma S, which is 172.06 into, you know, the area of steel. Since the steel wire is 1.3 square, so 3 mm. So naturally 172.06 into area of steel cross section. So which will going to be pi by 4 into 3 square. So that is area of steel, and the cross-sectional area is in terms of diameter. So where the diameter of a steel wire is considered to be 3 square, 3. Therefore, 172.06 into pi by 4 into 3 square. On simplification, you are going to get it as 1216.10. Similarly, load carried by the aluminium wire, which is PA, which is equal to sigma A into AA. So here, again, we have 96.354, which is the stress in the aluminium wire multiplied by area of the cross section of aluminium wire. Since the area of cross section of the aluminium wire is 5 square, so it should be pi by 96.354 into pi by 4 into 5 square, which will be equal to 1891.9 Newton. Then we have the distance moved by the rigid bar. So that means what is the deformation it is going to take by the rigid bar. So to do that, so elongation of the wire. So naturally, since it is the tensile load which is acting, so naturally it has to come down. So naturally it will going to have, since it is a tensile load, so naturally we are going to get the elongation of the wires, which is delta L, which is equal to, either you can use the formula of delta L of the steel wire or the delta L of aluminium wire. So to do that, again PS into LS by AS into ES. So again PS by AS is equal to sigma S into LS by ES, which is equal to, so we know what is the substitution value of sigma S, which is 172.06 into the length of the steel wire, which we know as 800, divided by the Young's modulus of the steel wire, which is 200 into 10 to the power of 3. So here, so this will going to get as 0.688 mm. So then the distance moved by the rigid bar, which will be equal to 0.6688 mm. So this is how you will be able to solve this problem. Thank you.